Good day, fellow. Setsu is back. And if you are new to this channel, please kindly don't forget to subscribe. Today, my fellow learners, we are going to do the new concept which is called momentum. Momentum. What does the concept momentum implies to us? It's m over there, it's momentum. What does the term momentum implies to us? It is the product of mass and velocity. You see now, we have two physical quantities over there. We have mass and also what? Velocity. Do you still remember from grade 11, if I'm not mistaken? We said that mass is a scalar quantity. The scalar quantity, meaning it only has what? Magnitude. See? Then we also said that the velocity is what now? It's a vector quantity. A vector quantity, meaning it has both what? Magnitude and also what? Direction. You see now? Then the concept of momentum is also what? A vector, which means it has both what? Magnitude and what? And direction. You see, the concept of momentum is also given by now P is equals to mv. You see, where P is momentum, where m now is mass. You see, where v now is velocity. We know from grade 10 as well as 11 that mass, its unit is kg, and then velocity, it's meter per second. From these two, we can then now work out the units of what? Of momentum by saying now, we know that mass measured in kg, then velocity in meter per second. Let me do it like this. You see, at the end of the day, the units for momentum is going to be kg meter per second. You see, and don't forget that momentum is a vector quantity. It also has what? Direction. Okay, now what I'm going to do now is, suppose if let's say they give us now a ball, you see, of let's say 2 kg, which is moving at the velocity of let's say 3 meter per second. Then they ask us to determine the momentum of this given ball. Firstly, we need to decide the direction, because the momentum is a vector quantity. We just need to say now everything that goes to the right will be positive, everything that goes to the left, let's make it negative. You see, to the right and to the left. Then from here we can then just take out our data. We have mass, we also have velocity of 3. Then we know that the formula to calculate momentum is given by mv. Let us substitute. We have 2, we have 3. Then 2 times 3, we get 6 meter per, sorry, almost made a mistake, kg there, meter per second. You see in which direction our answer is positive. You see, implies to the right. see, it's so simple, this thing. It's so simple. Let me give you another example. Let's say now we have another ball, you see, which is moving to the left with the velocity, let's say, of 2 meters per second. The ball, let's say it has mass of, say, of 2 kg. See, then I ask you to calculate the momentum for this one. How are you going to do it? So simple. You decide the direction, everything that goes to the left, negative, to the right, positive. Then we take out our data, 2. Then our velocity now, bear this thing in mind, that now this one is a velocity. You see, it's a vector quantity. We are going to say minus 2. You see, then let us substitute. We have something like this. Mass is 2 minus 2. At the end of the day, we're going to get minus 4 kg meter per second. From here, we can then just say 4 kg meter per second. In which direction now? Because our answer is negative, to the left. You see, it's so simple. Now, what is going to happen if now we were to take, let's say, a ball, a situation which is like this now. Let's say the ball of 2 kg, which moves with a velocity, let's say, of 4 meters per second. Then somewhere there, it strikes the wall and bounces back to the left. Let's say with the velocity of 2 meters per second. Bear this in mind, that the mass will always be the same. But now check the velocity. The velocity, it has changed now. Now we are going to introduce the new concept of change in momentum. You see why? Because of this velocity. You see, now we are going now to introduce the new concept. The velocity, it has changed from 4 to 2. You see, we know that change from physics implies final minus what? Final minus initial. You see, some learners goes further, even solving it by saying now m v final minus m vi. You see, either way is also fine. Then now, how are we going to calculate the change in momentum for the given scenario? It's so simple. We take out our data by saying now we have a mass of 2, because it's the same ball. Then v final, you must now include the sign, because this one is a velocity which goes to the left. It's going to be minus 2 v initial, which is now 4 to the right. You see, from here we can just do what? Substitute. From, let's take this formula, it's much easier. Going to say now, this is our formula. We substitute, our mass is 2, final velocity is minus 2, then formula is minus, then the initial is 4. Get 2, get minus 6. At the end of the day, we're going to get minus 12 kg meter per second, which is then now 12 kg meter per second. In which direction? Because we got a negative answer, say left. You see, it's so simple, isn't it? Okay, let us continue. Let me erase. I won't take long. Sorry. Okay, I'll be done just now. Okay, yeah. Let me also erase here. Do you still remember the second Newton's law of motion? Do you still remember that equation of second Newton's law? It was like this. F net is equals to ma. Do you still remember this formula? I know you do. Then now from grade 10, I can still remember. We said that acceleration is the rate of change in velocity. The rate of change in velocity. Let me just say time to avoid unnecessary things. Then acceleration is the rate of change in velocity. Where you see A, let us replace it with this formula, which now is V final minus Vi divided by time. You see? From here, we can just then do what? Distribute the mass throughout, which is then going to be V final minus Vi divided by what? By time. We have F net. Do you still remember that we said the formula for change in momentum can be written as, you see, where we see this one, we can then replace with this one. Then we are going to get the second Newton's law now in terms of what? In terms of momentum. You see, we are going to get the second Newton's law in terms of what now? In terms of momentum, which is like this. Then I just want to highlight something, which now we F net, which is F net. The net force is inversely proportional to what? To time, or the contact time. You must know this. You must know this. That if we decide to increase, or if let's say we increase the contact time, if we increase contact time, the net force will do what? If we increase this one, then this one will do what? Will decrease. They are inversely proportional. You see, same applies now. If we decide to decrease time, eventually the net force will do what? Will increase. See, if I take time, if we decide to take time now, changing P over T. If we decide to multiply throughout by time, we know this is going to cancel this. We are going to get something like this now. Let me start with F net, multiply by time. If we multiply by time, both sides, we are going to get something like this. We now call this what? The impulse. Impulse now. We now having what? Impulse. What does the term impulsory impulse implies to us? It is the product now of net force, and what? And contact time. Contact time. You see, it is the product of net force and contact time. We know that the unit for net force is newtons, which then going to be impulse. Let me say impulse. Net force is going to be newton, then times going to be second. You see the units for impulse, which is the product of what? Of net force and what? And contact time. We know that the time is a scalar quantity, net force is vector. Then from here, what I can do is, let me just give you this example. Suppose if you come across, let's say something like this. Let's say if I decide to give you a function, say net force this side, net force, then let's say somewhere here I decide to give you time. Say we have 2, 4, let's say 6, 2, 4, 6, everything in second. Then I decide to sketch a function like this. Somewhere there I give you a force, let's say of 10, then force in Newton. See? Then I ask you to calculate the impulse for this given function. How are you going to calculate the impulse for this given function? It's so simple. From this formula, we can clearly see that if we multiply net force with time, we get what? The impulse. You see, same applies. From this given function, we just need to find the area. The area of this thing is going to be what? Impulse. That means impulse is going to be the area of this function. You can then now do what? Can then now say impulse is going to be 1/2 base multiplied by height, which is then now 1/2 base is time. You can start, let me substitute time anyway, t, then net force, let me say F net. From here we have 1/2 times 6, our net force 10, then we have 0.5 multiplied 6 multiplied by 10. We get what? 30 Newton with second. See, then this is just how we calculate the impulse whenever they give us the function of net force with what? With time. Just wanted to clarify that. You see, my fellow? Then yeah, allow me to erase. I won't take long. Okay. Okay. I'll be done just now. Okay. done just now. You see, I'm done. Okay, fellow. Now, I just want to introduce to you again this concept of linear, let me say, the law of conservation of linear momentum, or the principle of conservation of linear momentum. You see, you still remember the law of conservation of energy. It states that the total energy in an isolated system, or the total energy, cannot be created nor destroyed, but it can be transferred from one form into another. You still remember those? Same applies. Let us see of linear momentum. It states now the total linear momentum, total linear momentum in an isolated system is conserved. See, you must know how to state this. It's very important. See, then now how do we calculate using the formula of conservation of linear momentum? It is like this. We have the sum of momentum before, which is equals to the sum of momentum after. See, don't be confused by these notations. You see, it implies now we have mv initial, let's say for object A, plus mv initial for object B, which then equals to mv final for object A plus mv final for object B. You see, don't be confused. For this concept of total linear momentum, of the conservation of linear momentum, we have three cases mostly. You see, we have a case whereby, let's say now, let me say case one. See, whereby two objects collide. Let's say this is before, then afterwards they go in opposite direction, like this. You see, they approach, then after they go opposite. See, after going opposite direction, eventually you get the formula, which is like this for this case. See, mv final plus mv final. You see, I'm going to make an example. Then another case is this one, whereby we have before now, let's say they approach somehow before, then after they stick together and move in one direction. For this one, we get something which is like this, is equals to, now they combine together and move with same velocity. You see, then we also have a situation which is like this now. Let me call it case 3, whereby now we have two items before, eventually afterwards they separate like this. Let's say this one goes that way, goes that way, but initially they were together like this. See, then afterward they split. Oh sorry, final. This one is initial. You see, they split like this. What I'm going to do is, let us consider a simple example. Suppose now, allow me to erase. Somewhere here. See, suppose let's say these two balls, they're identical. See, let's say they are identical. They are identical, each having, let's say, the mass of, let's say the mass of this one is 2. Same applies to this one. Let's say the mass of this one is 2. Somehow, let's say the velocity of this one moves to the right. Let's say vi, it moves to the right with the velocity of 1. This one, it moves to the left with the velocity, let's say, of 2. Then afterward, we know that the mass won't change. Let's say afterward, this one, let's say this one, it moves to the left with the velocity, let's say it moves to the left now with the velocity of -1. Then they ask us to find the velocity now of this one. Let's call this ball A, this one B. Let's go and find the velocity for ball B. How are we going to do that? You can just say, we know that the momentum is given by vi initial, which is going to be vi final plus m final for A, B. The mass is 2. Initial for A, velocity is 1, plus the mass for ball B is 2. The mass, they are identical. Then for velocity we had -2. The mass for ball A, we got, let's see, for ball A, the mass, oh, it's 2, don't change. Then the velocity got -1, plus the mass for this one is 2. Now we want to calculate the velocity of ball B. Let's solve. We have 2, we have -4. If we multiply this side, we are going to get -2 plus 2 what? V final for ball B. We are going to get -2. Or let me just take this 2 to the other side. It's going to be 2 minus 4 plus 2, which is equals to 2VMB. Then let us substitute. We have 2, let us solve. -4 plus 2. We are going to get 0, which is 2V for B. If we divide everything by 2, still going to be 0 meter per second. You see, that means this ball afterward, it won't move. it will remain like at rest, but this one will move towards the left, you see. Then another concept regarding this topic of momentum that you need to know is elastic and inelastic collision. Don't forget that we got 0 here, because I'm going to use it. We have elastic and inelastic collision. What do we mean when we say collision is elastic and also when is inelastic? Let me summarize it for you. When the collision is elastic, we have elastic to collision, elastic collision. For elastic collision, momentum is conserved. Firstly, momentum conserved. Then the sum, let me say, the sum of kinetic energy is conserved as well. Conserved, meaning EK initially is going to be equals to EK finally for, let's say, 2 objects. Then elastic collision momentum is conserved. Then sum of kinetic energy not conserved. I hope you can see the meaning EK initial is not equals to EK final. See? Then let us see if this collision is elastic or inelastic. We are going to do this. Don't forget that the formula for kinetic energy is given by 1/2 mv squared. You see? We are going to start with before. Going to say, EK initial before, going to be initial for both sum of kinetic energy before, going to be, let me see if I'm going to have enough space, squared plus 1/2 mv squared I. For ball A, says A is B. The mass was the same for both. We have 1 squared plus 1/2. The mass of B is still 2. You still remember 2. The velocity initially we had minus 2 for B. For A. See, I just want to make sure if I don't make any mistake over there. Then let's see what are we going to get. 0.5 to 1 squared plus 0.5 to -2 squared, going to get 5. Remember energy, you see, energy joules, kinetic energy joules. Then we also have now EK final. going to be 1 over 2. Do the same formula, but now going to focus final velocity. Then we have 1 over 2 in the mass, same is 2. Final for this one, we got minus 1 squared plus. Then we had 1 over 2, the mass for B, we had 2 same. But now, final for B, we got what? 0 squared. This side, we are going to get 0. Clearly, we are going to get 0. But when we take this one, we are going to get, I think, 1. 0, 0.5, 2, and negative 1 squared is 1. 1 joules. See? Let us compare these two values, 1 and 2. Are they equal? EK initially and EK final. Are they equal? Nope, not. Therefore, it's going to be what? Inelastic. Inelastic collision. See? I thank you and enjoy. Thank you.